Today we can start the second module and it deals with the shear stress and shear strain. Here we can see in the figure itself that the block is subjected to shearing force and the shearing surfaces are surface AB and CD. Because of the force acting on that block, then the shear forces developed on the shearing surfaces are V marked on the two sides. And due to this shear force, shear stresses are developed. We have seen the shear stress in the first module while discussing about various types of stresses. And the stress induced in a body when subjected to two equal and opposite forces which are acting tangentially across the resisting section, as a result of which the body tends to shear off the section, is known as the shearing stress, and it acts tangential to the area. You can see the shear force on these two given figures. Here you can see the expression for shear stress and shear strain. I have already explained this in first module while discussing about various types of stresses. Here I have considered an element of length L and height h, and it is subject to shearing force P. And the shearing section is marked here as XX, and the shearing resistance is R, and the shear stress is given by shear force divided by the shearing area, and the shearing area is L into 1. Then shear resistance is equal to the force acting tangential to the surface, so it is given by P into L into 1. Next we can get the expression for shear strain, that is the angular distortion. ABCD represent the initial shape, ABC1D1 is the deformed shape, and the angular distortion phi, that is equal to, in order to obtain the angular distortion phi, we can consider the triangle AD1D. Then tan phi is equal to DD1 divided by AD. When phi is equal to very small, tan phi is equal to phi. And phi, that is equal to DD1 divided by this AD, or that is the DD1 is the transverse displacement. We can represent it as DL, and AD, that is the height of the element. Height. So the shear strain is given by DL by H. And now comes the elastic constant shear modulus. Here the shear stress tau is proportional to the shear strain phi, and the constant of proportionality is G, which is the shear modulus or modulus of rigidity. And we can define the shear modulus G as the ratio of shear stress to shear strain. That can be represented as tau by phi. Then I shall show you some practical cases where the shearing occurs. For that we can consider a beam. Let this edge be hinged, and here let it be a tall support so that it is a simply supported beam. It is subjected to transverse load F here. We can consider a small element near to the support, and here for this element there are both the shear stress as well as the normal stress occurs. Normal stress, that's bending stress, is normal to the surface, and shear stress, that is a tangential to the surface. And corresponding to normal stress, we will have the normal strain, that is normal to the cross section, whereas because of the shear stress there will be shear strain which causes the distortion of that particular element. This is a beam subjected to loading. Then these two represent the supports. The loading, this load is transmitted to this beam through these 2 points, point loading, and this represents shear failure pattern. This beam fails by shearing. This is the shear failure of columns, tearing of the surface, and in soil usually the failure occurs because of shear. You can see the shear failure of soil, and this represents the failure surface. Then the shearing resistance of the retaining wall, that is less than that of the shear offered by this soil, so the failure occurs. Now we can move on to the case of simple shear. A material is said to be in the state of simple shear if it is subjected to only shearing stress. Previously in the case of beam, we have seen an element which is subjected to both shear as well as bending. Then there may be certain occasions when it is subjected only to simple shear. One of the examples is bolt is subjected to shear. In beam itself, we can adjust the loading conditions as well as the support condition such that a particular section, the failure occurs only because of shear. Then if the material is subjected only to the shear, it is known as the simple shear. Then, as you know, a shearing force tied to shear of the cross section of the body. You have seen the examples of beam, shear failure of beam, shear failure of column, etc. Now, this is the element ABCD under simple shear. That is, it is subject to only the shear stress. There will not be any normal stress acting. Then QAB, that is the shear stress along face AB, QBC, the shear stress along BC, QCD, shear stress along CD, and QAD, the shear stress along AD. And let the thickness of the element is T. Now we can consider the equilibrium of the element. We can consider both the horizontal equilibrium, vertical equilibrium. First, we can consider the vertical forces. Here we have the two shear stresses QAB as well as QCD. And the shear force on face AB, that is force is given by stress multiplied with the area. So the vertical force on AB, that is equal to shear stress on AB multiplied with the shearing area. Then the shearing length is AB and the thickness of the element is T. Therefore, the vertical force on AB is QAB into AB into T. Now we can consider the vertical force on CD, that is given by vertical force on CD, that is given by QCD into the area. Here the area is CD into T, length CD into T. And for the vertical equilibrium, that is sigma v is equal to 0, these two forces should be equal. Here it is acting upward in face AB and on face CD it is acting downward. So QAB into AB into T should be equal to QCD into CD into T for the vertical equilibrium. And we know that the length AB is equal to length CD. From this we can reach the conclusion QAB is equal to QCD and we can say that is equal to Q. Now these two shearing forces will give rise to a moment. That is two equal and opposite forces separated by a perpendicular distance. And here the moment lever arm or the moment arm is the perpendicular distance between them, and the perpendicular distance between the two vertical shearing forces is AD. And the couple or the magnitude of the couple, that is equal to force into perpendicular distance, that is equal to the forces Q into AD into T multiplied with the perpendicular distance, that is AD. Let this be equation number 1. Now let us consider the horizontal equilibrium. On face BC, we have the stress QBC, and on face AD, we have the stress QAD. And the stress on the face QBC gave rise to force, that is QBC into the area, that is QBC into BC into T, that is a horizontal force towards left side acting on face BC, and QAD into length AD into T, that is a horizontal force on face AD acting towards right side. And for this equilibrium, these two should be equal. Then QBC into BC into T should be equal to QAD into AD into T. And we know that BC is equal to AD. From this we can reach the conclusion QBC is equal to QAD, and let this be equal to Q dash. Now we have two equal and opposite forces on the faces BC as well as AD. This will give rise to a couple, and the magnitude of this couple that is given by force multiplied with the perpendicular distance. And the perpendicular distance between these two horizontal forces is AB. So the couple formed by these forces is Q dash into A into AD into T, that is a force, multiplied with the lever arm, that is AD. And this couple is in anti-clockwise direction, whereas a couple formed by the vertical forces, that is in the clockwise direction. And let this be equal to equation number 2. And for the equilibrium of moments, sigma m should be 0 for the equilibrium. We can equate the equations 1 and 2, which gives Q is equal to Q dash. That is a Q, that is the shear stress in vertical direction, that is equal to the shear stress acting on the horizontal planes. So it is marked here, all the shear stresses are Q, shear stress on the horizontal plane as well as shear stress on vertical plane, all should be equal. So we can say that a set of shear stress is accompanied by a transverse set of shear stress of same intensity. Here the one set is the vertical forces. Set of shear force means these two vertical shear stresses. It is accompanied by transverse stress of same intensity. It is accompanied by horizontal set of shear stresses of same intensity. This principle is called principle of complementary shear stress. And the element offering this stress is said to be the element in a state of simple shear. This is one of the important property. Now, let us consider the effect of these shearing stresses on a plane at an angle of 45 degree to the shearing direction. Now we are considering the element in a state of simple shear, that is at all four sides the shear stress is of same intensity, that is Q. Now we can consider a square element. Let the side of the element is A and thickness is T. A, B, C, D is our element. Now we can consider a section along AC because our aim is to obtain the effect of this shear stress on a plane which is at an angle 45 degree to the shearing direction. And here this angle is 45 degree, that is along the diagonal. Then let P be the stress, normal stress on this section. It is marked here. The normal stress is marked as P. Since the sides of the square is A, and we know that the length of this diagonal AC, that is given by A root 2. Now we can consider the equilibrium of forces in the direction normal to AC. Then because of P, the force normal to that one is P into cross-sectional area, that is P into AC into T. Now we have the components of both the forces on face DC as well as AD normal to AC. Here we can draw the components. These two forces, these two represent the components normal to the surface AC. That is QCD cos 45 into T plus QAD sin 45 into T. The direction of these forces are in this direction, which is opposite to the force due to P. So we can equate these two, and from this we can obtain the expression for the normal stress due to the shear forces acting on the sides. Then we can substitute for AC as A root 2, and we know that cos 45 is 1 by root 2 and sin 45 it is also 1 by root 2. So PA root 2 T, that is equal to QAT root 2, or P is equal to Q. Here, P is the normal stress on a plane at an angle 45 degree to the shearing direction. That is the stress normal to the face AC. And Q, which is the stress on the faces of the square element of side A. Since this element is under simple shear, the stress on all faces will be equal and it is represented as Q. Thus, in the case of simple shear, tensile stress of same magnitude as shear stress develop at 45 degree to the shearing plane. That is, the tensile stress is P, that is P is equal to Q. By taking the other diagonal, here we have considered the diagonal AC. If we consider the other diagonal BD, we can prove that there will be a compressive stress of magnitude Q acting on that plane. Thus, we can see that simple shear give rise to tensile and compressive stresses across the planes inclined at 45 degrees to shearing planes. Then the intensity of direct stress is same as that of the shearing stress. Now let us see what is plunging shear is. This usually occurs in flat slabs and foundation. Then plunging shear occurs because of the shear effect, and it is a brittle failure mechanism. Then in the case of ductile failure mechanism, which we prefer for beams, we get enough warning before the failure. These things that you will study in higher semesters. But the plunging shear is a brittle failure mechanism, usually occurs in slabs and foundation, and it is because of the action of concentrated load or highly localized forces. This is critical because in the case of brittle failure, there will not be visible signs prior to failure. So we can't take the measures for overcoming these types of failures. Then here, as you can see, diagonal tensile cracks will form due to this brittle failure. Usually in the case of frame structures, slabs are connected to beams and beams are connected to columns. And the load will transfer from slab to beam and then from beam to column. Whereas in the case of the flat slab, the column is directly connected to the slab and usually a column head will be provided. And the failure occurs due to the reaction of column against the slab. Here this represents the column reaction acting in this direction, whereas the load from slab acts in this direction. And because of these two, the failure will occur along these lines. That is the diagonal direction, and this will leads to the plunging shear failure. Whereas in the case of the foundation, the soil will exert the pressure in upward direction and load from the column will be transmitted to the soil through foundation in the downward direction. And failure may occur along these lines, leads to the punching failure of the foundation. You have to study these things in details in the higher semesters. And this gives us some examples of the punching shear failure. You can see that here the punching shear failure is occurring. Okay, thank you.